Oh, AP Stat students from around the country and also from around the world. And welcome to day 2 of the AP Statistics virtual instruction offered by the College Board. I sure hope that you got a chance to get online yesterday and check out my colleague, Brendan Murphy, who started us out yesterday with day 1. I'll be here with you today and tomorrow, and then we'll just be sort of switching back and forth throughout the rest of this instruction. My name is Luke Wilcox. I am an AP Stats teacher in Kentwood, Michigan. And if you're from Michigan, you pull out your map and you tell everybody where you're from. And so we're from West Michigan here, Kentwood in Michigan here. So that's where I'm from. And I'll tell you, we closed about 2 weeks ago at my school. And I was super bummed about it because some of the best lessons of AP Statistics come at the end of the year. There's a lot of candy activities. Students just love the end of the year. And I was super bummed that I'm going to miss that opportunity with my own students. So when the College Board reached out to me and said, hey, would you like to do this thing online? I was just super excited about it because now I'm going to get a chance to share some of those excellent lessons. But I will tell you, I'm a little bit nervous about this whole YouTube thing, this whole YouTube live. I'm kind of old, so I'm not super familiar with this sort of thing. So I checked with my 8-year-old son, Trey, and I was like, hey, Trey, what's this YouTube live thing? Like, do you think I could teach kids AP statistics? And he said, Dad, you're gonna be on YouTube live. You are gonna be YouTube famous, Dad. Well, I don't quite think that's gonna happen, but I like that my son is thinking that about me. So I do have one request of all of you AP Stats students. So listen, if you ever see me at the grocery store pumping gas, something like that, and I'm with my children, I'd like you to come up to me and ask me for an autograph and tell me that you saw me on YouTube, okay? Because I'd really like for my son to actually think that I am in fact YouTube famous, okay? So without further ado, let's go ahead and jump into the lesson for today. So just to make sure that everybody's in the right location, I hope that you are here tuned in to learn some AP statistics. You already know who I am. My name is Luke Wilcox. I teach at East Kentwood High School in Kentwood, Michigan. I have been a teacher there my whole teaching career of 19 years. And 15 of those years, I've been teaching AP Stats. So I do want to take a quick moment to give a shout out to my East Kentwood High School Falcons. So what's up to my first and second hour AP Stats? Also want to say hello to Miss Gallis's third hour and fourth hour AP Stats. I hope all y'all are doing excellent and that you're safe and you're home with your families. Now, in terms of AP statistics, I do have quite a bit of experience teaching it at 15 years, but I've also been an AP exam grader for the last 6 years. And so I'm definitely going to try and bring some of that expertise and knowledge to the lessons that I'm going to bring you. Some of the sort of insider information that you learn when you sit for 8 hours a day and grade student papers. So I'll try to share that as much as I can with you. I also do a whole lot of training with AP statistics teachers around the country. I've been a College Board consultant for AP statistics for several years now. Now, a couple of quick reminders. I know that Mr. Murphy talked to you about this yesterday, but I just want to reiterate the schedule for us. We are in the 6th hour time slot, and that means that 2 o'clock to 2:45 every day. We're going to be meeting Monday through Friday. Just to give you a heads up on the schedule, March 25th through April 3rd, we will be covering units 8 and 9, which is most likely not something that your teacher taught you before you left school. This happened to be exactly where we left off at East Kentwood High School. We did 1 day of chi-squared tests and then we were out. So that's the last 2 units here. And very, very important, I want everyone to know this, Unit 8 and Unit 9 are not going to be on the AP exam for the 2020 school year, okay? So this is intended to be out there as an optional thing for you to be able to learn, to take with you forward into college. But it is important for you to know that this content from this week and next week will not be contained on your AP exam that you'll be taking this year. Then on April 6th, we are going to officially start the AP exam review. And that is going to be very specific very targeted to getting you ready for the AP exams. I'm really excited about that. Now, all of the resources that you might need, which would include the lessons that we're going to be teaching, as well as the short, very short homework assignments that we're going to be giving you, you can find at statsmedic.com/YouTube. There's actually a link. If you look in YouTube right below me here, there's a link that you can click, and it will take you to those resources. They're organized by date. So today is March 26th. You will see March 26th listed there, and you can click and get the lesson that I'm going to be teaching today, as well as the homework assignment that I'm going to be giving you at the end of this lesson today. Okay, so I am going to start with your homework from last class period. This was given to you by Mr. Murphy. This is a multiple choice question from an old AP exam. And so let's just take a look. And I'm going to read it out loud for you first so you can remember what it was about. It says, in order to plan its next advertising campaign, the Trendy Motor Vehicle Company is investigating whether the type of vehicle and the color of vehicle are related. Each person in a random sample of size 275 selected from the company's mailing list was classified according to the type, car or truck, and the color of the vehicle he or she drove. The data are shown in the table below. Which of the following procedures would be most appropriate to use for investigating whether there is a relationship between vehicle type and color? So I'm going to use a little bit of a multiple choice strategy here, and that's to just go through each answer choice and think about whether that answer choice makes sense here. So when I look at answer choice A, a 2-sample t-test, that means I have to have 2 samples, and it also means that we're going to have to be calculating means for each one of those 2 samples. For a 2-sample z-test, well, that's really the same thing, 2 samples dealing with means, but this time, for some reason, we know the standard deviation of the population. The third one, a matched pairs t-test, we'd have to have some paired data there where we'd be looking at differences, and we would want to find the mean of the differences. So right away, I'm noticing that in these first 3 answer choices, we're dealing with means, which would mean that we need quantitative data. Now, this is going to be different than the next 2 that you see. They're both chi-squared, which you know that's what's coming here, right? That's what we're going to be teaching this week is chi-squared tests. And chi-squared tests, both of these are going to require that we have categorical data. Now, a little bit of a preview of what's to come, because today we're going to be doing goodness of fit. You'll see the test of independence with Mr. Murphy on Monday. But here's the big distinction between those 2 chi-squared tests. For a chi-squared goodness of fit test, you're going to have 1 population, and you're going to be measuring 1 variable. And we said that that variable is going to be a categorical variable. Now, a chi-squared test of independence, you're still going to have 1 population with 1 sample, but now you're going to be measuring 2 variables for each individual in the sample. So let's go back to the question here and see which one of these answers actually makes sense. So I do see here that we had a random sample of size 275 from the company's mailing list. And to me, that sounds just like we only have 1 sample here, which I think is telling us that we have 1 population that we're sampling from. So really right away, A and B are out because this is not a 2-sample problem. The next thing I notice here is that the variables that we're measuring here, vehicle type, vehicle color, 2 variables, both of which are categorical. So certainly C is out because we need some quantitative data there, and we're left with these 2 chi-squared tests to decide between. And because we have 2 variables here, we definitely know that answer choice E is going to be the correct answer here. That's 1 population with 2 variables, chi-squared test of independence. And you're going to learn a whole lot more about that test on Monday with Mr. Murphy. Now, I do want to give you one other little clue that we had. In the wording of the question, it talks about the relationship between 2 variables. Another word that we could use instead of relationship there is association. And anytime you see that word relationship or association, that is an indicator to you that that might be a chi-squared test for independence. So I hope you did okay on the homework assignment there. And I think we are ready to jump into today's lesson. And what I'm going to do is I'm always just going to start with a quick overview to let you know like sort of where we're headed within that particular lesson. And the way that I like to organize things is with very specific learning targets. And the reason I like this is because we can come back to these learning targets at the end of the lesson and make sure that we've actually accomplished these 3 learning targets. So let's just check in here. Learning target number 1 is to calculate expected values for a chi-squared goodness of fit test. The second learning target is about conditions, the random, 10%, and the large counts condition for a chi-squared goodness of fit. And then finally, by the end of this whole thing, we need to be able to do a full significance test. And I'm going to show you the way that I organize it using a 4-step process of state, plan, do, conclude. So we will check back in with these learning targets at the end of the lesson to make sure that we've learned what we needed to. Okay, so this is the actual lesson you're going to see here. And this is available on the website at statsmedic.com/YouTube. You can download it. Or if you just want to write on some notebook paper, you can keep track of where we're headed with this. Okay, so the ultimate question of today's lesson is which color Reese's Pieces is your favorite? And I'll tell you, my daughter, she's 11 years old. Her name is Reese. And sure enough, her favorite candy in the world is Reese's. And she actually noticed one day that she was eating a Reese's Pieces, and she noticed that there seemed to be a lot of orange Reese's Pieces. And I had thought that they were equally distributed, yellow, brown, and orange. They give you the same amount of each one. So I took a look on the internet, and according to the internet, the company claims the following distribution of color. So you take a look here, 25% brown, 25% yellow, and like my daughter thought, they're claiming that actually half of them are orange. So I'm going to give you just a little bit of a heads up here. What we're starting with this distribution of color that we're looking at here, this later is going to become our null hypothesis. And we'll have a couple of different ways of writing that. And one other thing that I want to point out here is that my daughter and I, we went ahead and we took a random sample of Reese's Pieces out of one of those big bags. So we had one of the huge bags. We took a random sample of 50. Those Reese's Pieces are the one population that we're going to be dealing with in this problem. And we're looking at the variable of color, which is a categorical variable, one categorical variable. And we know from the homework problem that we just went over that if we have one population and one variable, that this is going to be a goodness of fit test. So let me give you the details about what we found. So we took a random sample of 50 Reese's Pieces, and go ahead and let's write down our observed counts. We got 13 that were brown, we got 7 that were yellow, and we got 30 that were orange. And I think it's important to note right now that the total of these is 50. That was the sample size here was 50 from this large bag of Reese's Pieces. And so right away, my daughter noticed that we didn't get a whole lot of yellow in our sample. There's only 7 in the yellow there. And we're supposed to get 25% of them that are yellow. So that seems a little bit low at 7. And then she also noticed that 30 was a little bit high because she knew half of them were supposed to be orange and half of 50 would be 25. So right away, because those values aren't exactly what was claimed by the company, we do have some evidence that the company was lying about their claimed distribution of color. Okay, some evidence. Now later on, we'll talk about whether we have convincing evidence by using a significance test. So let's take a look at the expected counts here. And very important, if we're going to be calculating the expected counts, we're going to have to assume that this null hypothesis is true here. So assume that the company is actually telling the truth. We want to calculate the expected counts. Well, for the brown Reese's Pieces, we know that there's 50 total, and they're telling us that 25% of them should be brown. So if I take 50 and I multiply by 0.25, 25%, that's going to tell me that the expected number of brown Reese's Pieces would be 12.5. Now for yellow, of course, we're going to get the same thing because 25% of them should be yellow. So we're going to get an expected value there of 12.5. Now for orange, the company claimed 50% of those. So if I take 50, my sample size, and I multiply it by 50%, that's telling me that I should be getting 25 orange Reese's Pieces in this sample of 50. So as expected, or as we sort of mentioned earlier, the number of yellow that were observed is less than would be expected, and the number of orange is a little bit higher. So I do want to point out here a formula. We've calculated an expected value here, and the calculation is really the same for each one of the colors. We're taking the sample size and we're multiplying it by the proportion. Sample size, proportion, sample size, proportion. So out in the margin here, I'm just going to make note of what we should have learned from that, and that's that the expected value is really just the sample size n multiplied by the proportion for that particular color, right? Where the sample size n was 50. And hopefully this formula looks familiar to you. If you think way back to the binomial distribution stuff that we did, where we were counting the number of successes, this actually gave you the expected number of successes. Now, I know some students might say, well, look, we can't have a half of a Reese's Pieces there. But it turns out that because this is an expected value or a mean, the decimal is okay there. So we can definitely leave our 0.5. We don't have to round our values here. So let's see if we can calculate the chi-squared test statistic. Now, from yesterday, Mr. Murphy told you the formula for the chi-squared, which is provided for you on the formula sheet. It is the sum of the observed values minus the expected squared, all divided by the expected. So let's just go through each color and calculate, plug in our numbers here and see what we get. So for brown, the observed number of brown was 13, and the expected was 12.5, and then we square it, and then we divide that by the expected value of 12.5. Now we move over to the yellow, and for yellow, our observed was 7, and the expected was still 12.5. And then for the orange, we had an observed value of 30 with an expected value of 25. And so I actually went ahead and put these in my calculator. Let me give you the values here. So this first value is 0.02. The second value is 2.42. And the third value is 1. And the total of that is going to be 3.44. Now, I do want to take a look at each one of those individual components. We call these the components of the chi-squared. And you'll notice that this first component is very small, almost 0. And the reason is, if you look at the calculation, the observed value and the expected value were nearly the same, right? 13 was almost exactly the same. So when you subtract it, you're going to get a very small number there. And then you're going to divide it by the expected. You're going to definitely end up with a small component there. Now let's compare that to the value right next to it, which is much, much larger at 2.42. And the reason is because our observed value was actually pretty far away from the expected value of 12.5 there. And then the third one's sort of in between. And you'll notice that the difference between the observed and the expected on this one is 5, almost the same as what it is from the previous component. But because the expected value was higher, relative to the expected count, we're going to get a smaller value for chi-squared there. Now, I just do want to make note here, I'm trying to pull out the important information. The thing that we needed to calculate our chi-squared test statistic here is the formula O minus E squared all over E. So let's just make note of that in the margin there. Okay, I think we are ready now to check our conditions before we can perform a significance test. Hopefully you're very familiar with checking conditions, doing that with inference for proportions and inference for means. And the first two conditions are going to look very familiar to you, the random condition and the 10%. And you've probably even seen the large counts condition, but it's a little bit different here. So let me get into the details of each one of these. So for the random condition, we know that we need to check that we have a random sample. And I told you that my daughter and I took a random sample of 50 Reese's Pieces. So let's just note that we did in fact have a random sample of 50. The 10% condition is something that we have to check anytime we're sampling without replacement. And my daughter and I certainly didn't take one at a time and replace them back into the bag before we chose the next one. So we are sampling without replacement, which means we need to check the 10% condition so that we know that the independence is satisfied. And that's to say that the sample size, which was 50, is less than or equal to 10% of the population size. Now, the population here is all of the Reese's Pieces in that large bag. So all Reese's Pieces in the large bag. And we're going to have to assume that there's at least 500 of them in that bag, and I think that's a reasonable assumption. So we can say that the 10% condition is satisfied. All right, now the large counts condition you likely saw when you were doing inference with proportions, and that said something like n times p and n times 1 minus p were greater than or equal to 10. Okay, similar here, we're going to look at the expected counts, just like we did for proportions. It was the expected number of successes and failures. And we need to find the lowest expected count. Well, our expected counts, if you look back up here, 12 and a half, 12 and a half, and 25. So 12.5 is the lowest of the expected counts. And we need to check that all the expected counts are greater than 5. And this is certainly true here. So all expected counts are greater than 5. So we have satisfied our 3 conditions here, which means that we can move forward with our significance test. So let's get down here to number 3, and we're going to see if we can calculate the p-value. So for this test, the degrees of freedom is n minus 1, and I'm going to guess that this looks familiar to you because you use that same formula when you were dealing with inference for means. But there is a very important distinction to be made here, and it's about what this n represents. Because in the past, when you were dealing with means, n represented the sample size. But here, very important, that represents the number of categories. So I actually don't even like to write the formula with n in it. I would rather you just write the formula as the degrees of freedom is the number of categories minus 1. That's for a chi-squared goodness of fit test. So in this particular case, the number of categories, well, we had 3 different colors that we could get for the Reese's Pieces. So 3 minus 1 is going to give me a degrees of freedom of 2. So the test statistic, we've actually already done the work for this one, right? That's the chi-squared value, which we have from above as 3.44. Now we need to be able to turn that into a p-value. And I'm giving you the hint here that you have to use table C in order to find the p-value. Now this table C would be provided for you on the formula sheet. So I've actually just pulled up the formula sheet from the AP exam here, and this is what table C looks like. And it's likely that you've probably already done some work with table A and table B, but table C is going to be what you need for any of the chi-squared tests here. And here's the way that it works. The first thing you need to know is your degrees of freedom. And we had decided already that number of categories minus 1 is going to give us a degrees of freedom of 2. Now what you're looking for is you're looking for your chi-squared test statistic. And for our data, the chi-squared test statistic is 3.44. Now you're not going to find exactly that value, but let's see if we can get close. All right, I'm looking across the row. I'm looking at degrees of freedom 2, and I see 3.22. And I see 3.79, and I know that my value would be somewhere in between there, right? 3.44. And what this is telling me is that the p-value, or the area, this area that you see in the chi-squared distribution, that area has to be between 0.15 and 0.20. So that's telling me what my p-value is. So let's go back to the activity, and let's fill in our p-value there. The p-value is going to be somewhere between 0.15 and 0.20. Now that's nice. I like table C because it gives me an idea of what the p-value is, but I'd actually really like to know like the exact p-value. And there is a calculator function which will allow you to calculate the exact p-value for a chi-squared distribution. So if you could grab a calculator, or you can just follow along on the screen here. I've got my calculator pulled up. I'm going to show you where you can find this on the calculator. Okay, so the menu that you're going to need here is you're going to need to go to second vars. So second vars, that's going to give your distributions menu. And it's likely that you've used this menu in the past. I'm going to guess that you probably have used normal CDF and probably even TCDF to find the area under a normal curve or area under a t-distribution. But we have a chi-squared curve. So you're going to have to scroll down until you get to chi-squared and make sure you're using CDF, cumulative distribution function, rather than PDF. Go ahead and hit enter. And sure enough, I have my numbers saved here. The lower bound for us, that was our chi-squared test statistic, 3.44. The upper bound, essentially, you need to go to infinity. So I've just gone to 99999. Change your degrees of freedom to 2. And then you can scroll down to paste. That'll put it on the main screen for you. You hit enter. And there is our exact p-value of 0.179, which, by the way, is consistent with what we said in table C, where we thought it was going to be somewhere between 0.15 and 0.20. So now that we got that value from the calculator, let's go back to the activity and record that exact p-value, because I'd prefer to have the exact p-value rather than a range of values. So let's just record here that the actual p-value, and this is from the calculator. So make a little note to yourself that this is from the calculator. And the command that we used there was chi-squared CDF. So if you could write that down. And the p-value that we got from the calculator is 0.179, which I like that a little bit better than I like what we get from table C there, because we know the exact p-value. And we are now finally ready to make a conclusion. Now this p-value is a relatively large p-value, definitely greater than 5%. And so what this is saying is that this result could have happened purely by chance, right? Just because of the random sampling here. And it's likely that your teacher has trained you a little bit on how to write these conclusions. So let's see what this format looks like here. We're going to say, because this p-value that we just calculated, the p-value of 0.179 is greater than the alpha level, which we're just going to go with 0.05 by default. Now we have to make our decision here, and this is where we're going to fail to reject the null hypothesis, which we had stated up above is the company's claim is true. That's the null hypothesis, which we are going to fail to reject. And we do not have convincing evidence that the company was lying about the distribution of color. So even though at the beginning there we said that we did have some evidence that they were lying about their distribution, we do not have convincing evidence, because the results that my daughter and I got could have happened purely by chance about 18% of the time. Now we do have one final question here on the activity, and it's asking which color of Reese's Pieces had an observed value the farthest away from the expected. And I had commented on this already, but it's definitely yellow. It was much less than expected. We had 7 yellow in our sample. We were supposed to get 12.5. And so that one was pretty far away, a little bit farther away than the other values there. And so it does make sense a lot of times at the end of these chi-squared tests to go back and like look at this chi-squared calculation here and see where the largest component is. And for sure, our largest component is here because the yellow was much less than expected. We call this a follow-up analysis. So I'm just going to make a note here that this is a follow-up analysis. But I'm going to say, too, that it's not all that important to do a follow-up analysis if the results that you got were not statistically significant. This would certainly be more interesting if we had statistically significant results. So in general, I would say that this follow-up analysis is really only necessary when you reject the null hypothesis, right? When you have statistically significant data. Okay, so that completes the activity here. Now, the thing I'd like to do next is I'd like to try and formalize this a little bit more on the next page. So this is where I'm going to introduce you to the 4-step process for writing up a significance test. And we really have all of the pieces that we need. They're all here. We just have to be careful about how we format those. So go ahead and flip to the next page. And this is where we're going to write up our full significance test using the state, plan, do, conclude template. And I've provided some little hints here about things that we need to make sure that we include. So let's start out with the state. We're going to need a set of hypotheses here. And we're going to start with our null hypothesis. And we already said this on the previous page. It's to say that the company's claim was true. So I'm going to say that the company's claimed distribution of color is correct. And then the alternative hypothesis, this is what we were trying to find evidence for, is that their claim, that they were lying about that claim. So I'm going to say that the company is lying about their claim. Now, that's not the only way to write your hypotheses. You could write them in symbols as well. So let me just make note of this. The other way that you could have written the null hypothesis is to talk individually about all 3 of the proportions, because if their claimed distribution of color was correct, then the proportion that were, let's see, brown, I'm gonna write it P subscript B, was 25%, and yellow was also 25%, and orange is 50%. So we could have actually written it out in symbols there. Now, if you do that, you do have to specify what these parameters are. So you'd have to say what that P is, like P with the subscript represents the true proportion of Reese's Pieces of that color, which is a little bit more work, right, to have to identify those parameters. Now, the alternative would be that these proportions are not correct. And so you think, well, okay, what if one of them is incorrect? Well, if one of them is incorrect, that means it's a little bit higher or lower than what is claimed. And one of the other proportions is going to have to adjust for that, because the proportions have to add up to 100%. So I'm going to say here, at least 2 of the proportions are incorrect. That would be the alternative. Now, I'm generally going to stick with the hypotheses written in words, and you're going to see that in the next couple of days when we do the other 2 types of chi-squared tests. Now, also included in the state here is the significance level alpha. We were given a value right here. This alpha value is 0.05, so I'm just going to carry that down. Okay, name of the procedure. Well, I hope you know at this point what we're doing here is a chi-squared goodness of fit test. And you will sometimes see that written as GOF, G-O-F, and actually you'll see that on the calculator. Okay, so let's go ahead and check our conditions here. We already did this on the previous page, so I'm going to just say here, let's say see previous page. And that's the random, the 10%, and the large counts condition, which we've already done that work. Okay, now, the do part is where we actually do the calculations here. So I do want to show you the work that would be required with this. I'm going to start by just writing out the formula, and this would come from the formula sheet from the AP exam. And we showed this work on the previous page, but I'm going to carry it over here because I want to connect it to the picture that we're about to draw here. We had 13 that were brown, and we expected 12.5. We had 7 that were yellow, and we expected 12.5. And we had 30 that were orange. We expected 25. And when we added that all up, we got a chi-squared value of 3.44. So I'm actually going to carry that over here. The chi-squared test statistic is 3.44. Write that over here. Now let's talk about the picture of this, because we didn't talk too much. I showed you table C, but I didn't talk about how this chi-squared distribution is a little bit different than a normal distribution or a t-distribution. And you saw it in table C in the shape of the figure. So let me just like make a little bit of a picture here to show you what a chi-squared distribution looks like. And there are several different chi-squared distributions depending on your degrees of freedom. Okay, we've got degrees of freedom 2 here, and actually with degrees of freedom 2, the chi-squared curve looks something like that. That's degrees of freedom 2. Now, if I were to increase my degrees of freedom, right, the number of categories increased, you're going to end up with a distribution that looks maybe something like this. That would be maybe degrees of freedom 5. And then let me draw one more for you. If the degrees of freedom was even bigger than that, it wouldn't be quite as tall, and it would go further off into the right. Let's call that degrees of freedom 10, right? And the important thing to notice here is that this value is 0, right? The lowest possible value you could get for chi-squared is 0, and that's because if you look at the formula, you're always going to get a positive value there, right? We're squaring things, and when we square things, everything becomes positive. So you can't get a value less than 0. And then the other thing to notice is that these distributions are all skewed to the right. Although I will say that as the degrees of freedom increases, it becomes a little bit less skewed to the right, okay? Now, for our problem here, let's draw our picture. We have degrees of freedom 2, which we know is this one that looks like this. I'm going to clearly identify that this is a chi-squared distribution, and I'm going to clearly identify that the degrees of freedom here is 2. And I'm going to go ahead and put in our chi-squared value, which we had calculated as 3.44. And this right here is the holy grail, people. This is the p-value. This is what we need in order to make our conclusion. And we actually did this work already, right? We did it on the calculator. We got a p-value of, what was it, 0.179. Now, I try to get in the habit of putting a box around the test statistic and a box around the p-value. Those are two very, very important things in the calculation. So I just want to highlight those. And we are now ready for our conclusion. Now, we did write a conclusion on the previous page, but I'm going to add one more sentence to the front end of it. And it's all about the holy grail, okay, the p-value, and knowing what that p-value actually means. Okay, so here we go. The interpretation of the p-value. Assuming the null is true, right? Anytime we do a significance test, we start by assuming the null hypothesis is true. And in this case, that means that the company's claim is true. So assuming the null is true, there is a 0.179. There's the p-value, which we know is a probability of getting. Now I'm just going to go back to my picture here, and I'm going to put it in words. It's the probability of getting this value for chi-squared or greater, right? Of getting a chi-squared value of 3.44 or greater purely by chance, right? When taking a sample of 50 Reese's Pieces. Okay, now that's a pretty high p-value, pretty good probability that that could happen purely by chance. And that helps us with the second sentence in our conclusion, which we've already written. I'm just going to carry that over. I'm going to say because the p-value, which is 0.179, is greater than the alpha level of 0.05, we fail to reject H null, and we do not have convincing evidence. I'm going to give you a little bit of a trick here. When you're trying to write the end of your conclusion, if you actually go back to the wording of the question, we're looking for convincing evidence that the company was lying about the distribution of colors of Reese's Pieces. That's all I need down here. So convincing evidence that the company was lying about the distribution of color for Reese's Pieces. Okay, and that's it. That's the end of our 4-step process for a significance test, chi-squared goodness of fit test. Now, I do have one last question here. What parts of the usual 4-step process are missing? There is a few things to note that are different in this significance test than the ones that you've done previous in the course. And just make note of these. There's no defining the parameter if you use that first version of the null hypothesis, right? If you're writing this out in words, you don't have to define parameters. And then the other thing is that there's not what I call a general formula for the test statistic. We just have the specific formula, whereas the other significance tests all sort of follow the same general format of statistic minus parameter all divided by the standard deviation. Okay, let's see if we can wrap things up here. So this is the important part, the important ideas. This is where I go back to the learning targets and make sure that we've hit all three of our learning targets. So learning target number 1 was that we were able to calculate expected counts for a chi-squared goodness of fit test. And we did arrive at a formula for expected counts, and that is n times p. Well, let's record that. The second learning target was that we needed to be able to check the conditions for this goodness of fit test. So we had 3 conditions here. Let's record all 3 of them. Random, which is to check to make sure that we have a random sample so that we can generalize to the whole population. When sampling without replacement, we need to check the 10% condition. So that's that the sample size is less than or equal to 10% of the population. And the large counts condition, which for this test means that all the expected counts are greater than 5. Okay, finally, learning target number 3. This is where we got to the 4-step process for writing up the significance test. And just a couple of things I want to highlight here in the important ideas. First of all, the null hypothesis in general is going to say something like the claimed distribution of something. Now we had color, but it's just whatever categorical variable that you're measuring is correct. And the alternative hypothesis is going to say that the claimed distribution is incorrect or is different. So that's in general what our hypotheses are going to look like. Just to draw a quick picture here to remind us that the chi-squared distribution is different than these other 2 distributions we've dealt with in this course. Should be skewed to the right, starts at 0. This is chi-squared. You do need to know your degrees of freedom, which we've decided is the number of categories minus 1. I'm also going to record here, even though we've written this a couple of times, the formula that we need for the chi-squared test statistic is observed minus expected squared, all divided by the expected. And of course, we would use this picture here to find the holy grail, the p-value, which allows us to make a conclusion to the significance test. Okay, so I do have a homework assignment for you. It is 1 problem. It is very quick. I'm going to be with you again tomorrow, so I will actually check in on this problem tomorrow. It'll be what we start with tomorrow. It's a modified version of an old AP exam question. You can also find this to download on the website statsmedic.com/YouTube. So go ahead and give that a try before we have class tomorrow. And let's see. Okay, there's that homework problem. So you can download that. We are approaching the end of our time here. And I certainly appreciate that you have tuned in with me today to learn about this chi-squared goodness of fit. And I hope that you're going to tune in every day from here on out. I will be with you tomorrow to discuss the chi-squared test for homogeneity. And then Brendan will wrap up the chi-squared stuff on Monday with the chi-squared test of independence. Now, before you go, I have some really important information to give you about the AP exam, okay? The College Board realizes that this is going to be an at-home exam, and you have to have access to a device with the internet in order to be able to take your AP exam. And they realize that there are some students that do not have access to that. And of course, it may not be you, but it could be one of your classmates. And listen, I want to make sure that every kid has access to taking this AP exam, regardless of whether they have internet or they have computers or a phone. So listen, if you know somebody who does not have access to a device or to the internet, can you send them this link? And there's a form that they can fill out, or you can fill it out for them, and we'll make sure that they have something, because we really want this to be equitable, and we need every kid to be able to access this AP exam in these crazy times here. So please share that with anybody that you think might need it. So once again, thank you all for tuning in, and I hope to see you tomorrow at 2 o'clock. Make sure you have your homework done, and we will see you then.